So the last talk of this morning session is by Silvia Nagy, and she will talk about extended phase space for sub-n-leading soft theorems. So the stage is yours.
Okay, yeah, so thank you very much for the invitation to this very impressive conference, both in quality and in quantity. So I'm going to change topic quite dramatically now relative to what we've heard before, and tell you a little bit about basically asymptotic symmetries and soft theorems. And as you've seen already from the very nice review talk by Laura and also by the quite a number of both plenary and parallel sessions on this, asymptotic symmetries, they've been studied quite a lot in recent years, both because of very nice applications to scattering amplitudes that we'll see later, and also because they're expected to play a central role in some proposal of flat space holography. But more recently, and what this talk will be mostly trying to look towards is subleading, the subleading soft theorems that I'll explain in a moment, and also loop corrections a bit less. And many people have contributed to these, and many of them you've seen nice talks on them already. So just a very quick overview. The soft theorems are just a statement of taking a scattering amplitude in n+1 legs, taking the energy of one of them to be very small. And then the leading term had been known for a very long time. And what we mean by subleading is this expansion in the energy where terms become more and more subleading. And there's a universal part where we have this nice factorization of some soft factors and then an endpoint amplitude. And then there's also some possibly non-universal terms in there that I will say a little bit more about these a bit later in the talk. So as an example, let's look at just the subleading order which you can extract. So this is just a little trick. If you look at this expression here, you can see that you can just isolate your subleading one with this operator. And this was shown to arise as a word identity for some of these asymptotic symmetries, but they're what we call overleading. So all of this stuff, I'll have a diagram later, I should have put it earlier, happens at null infinity, right? So our fields, you know, they fall off in a nice way that's dictated by very basic physics, that their components should start at order 0 in the R expansion. However, it was found that, you know, in order to get these word identities for this subleading one, we need a gauge parameter that actually starts at order R. So then you can see immediately from just comparing these two equations here that we can't really realize this as a symmetry transformation of our gauge field as we would expect. So the goal is then to extend our phase space such that these symmetries, which are crucial to amplitudes, can act canonically. So they're really symmetries, they're really acting on something where they are allowed to act. And then this, I think, we've kind of managed to do quite nicely. Goal 2, which is very much more at the early stages, is whether how much more this can feed back into the soft theorems. So let me start with the setup. So we'll be working just in Yang-Mills theory for now. I'll say a little bit at the end about gravity as well. And let me allow an arbitrary gauge choice. The procedure works actually in arbitrary coordinates, but if it helps, you know, you can just think of that we're working in Bondi, the usual Bondi coordinates. We also allow a very general expression for the gauge field. So maybe more generally, you think of the gauge field as expanded, you know, in powers of R, starting at 0, 1 over R, etc. We also allow log terms. So these can arise in certain gauge choices when you look at loop corrections, etc. So we want to be as general as possible. This is called a polylogarithmic expansion. And then the phase space, I was a bit schematic here, consists of just sort of the initial data you put at null infinity in order to get all this field. So this is just a basic setup. Then, as I was saying, I want to now introduce these divergent gauge parameters. So the standard leading order gauge transformation that we've seen in many talks, and you see in Strominger's review, is just this guy it's just at order 0 in R. In general, it'll depend only on the Z and Z bar, and of course it can act very nicely directly on the gauge field. However, as I was saying, we want to look at more divergent gauge parameters. So we do this very general expansion, of which the slide I was showing you earlier is just one example. So this this R, R and 0 is just one example. So here we're allowing ourselves to be very, very general. It can even be field dependent in certain gauges. This we have in the paper, but I've omitted it for the talk because it gets very, very ugly. And of course, it violates the fall-off. So then the solution is that in order to realize it as a proper symmetry, of course, we will need some new objects that it can act on. And the way to introduce these new objects in a nice algorithmic way is to think of the problem as a kind of symmetry breaking problem. So it's not a standard symmetry breaking, but it is in the way that I can't realize my symmetries. And if we think of it in that way, then we can use a very old trick called the Stuckeberg trick, which originally, many people are probably familiar with it, was used to restore some broken local symmetry, for example, in massive theories. Here, the situation is a little bit different, but it turns out that we can adapt it to our problem. The main kind of feature of the Stuckeberg trick is that you take the gauge parameter for the symmetry that you can't realize, and you promote it to a field. So what we do is we take this lambda plus, so this guy with a bad fall off, and we promote it to a field psi, which has exactly the same fall off in R and log R as the lambda that we had before. And then we say that the coefficients of this psi have to be part of our phase space now. And this will be a Goldstone type field, as we'll see in a moment from its transformations. Good, so let me tell you a little bit more about these fields and how we think of them. So one way to kind of understand them is that they come from the bulk. So remember, the way you do the Stuckeberg trick is that you take the transformation that doesn't work, you apply it on the field. So what we do is we construct this, what we call a dressed gauge field, where I've just done the standard gauge transformation on it, but you see instead of the parameters, I have these psi's now. Then the consistency condition, so this object for now is defined in the bulk, right? Because these guys have various different fall-offs. So these are divergent, and A is the original gauge field. Now the consistency condition is that this dressed object transforms just like a standard gauge field under a combination of the leading order gauge parameter and these divergent gauge parameters that we've introduced. I'm ignoring the standard small gauge symmetries because they don't do interesting things for us. Now the point is that I'm not changing the transformation of my original gauge field, and all the overleading transformations with lambda plus will act on the new psi, the new Stuckeberg field that I have. And imposing this sort of very natural consistency relation, using this information after turning the crank a little bit, one can derive the transformation rules for these Goldstone guys that we've introduced. And it turns out that they're governed by this curly O operator, which looks a little bit scary at first sight, but it turns out it's just what appears naturally when you do variational principles on these exponential guys. And you can expand it in terms of something called the Bernoulli numbers that appear in the expansions of Todd polynomials. And it has this nice expansion, and add here is just the adjoint action. So schematically, you should think of it as many, many commutators acting on this parameter here, and they are organized in terms of the order in psi. So you see this many, many commutators with different orders in psi. Good, so let's just see two kind of interesting features, one of which we understand, one not so much yet. So at zeroth order, so this is the transformation of my Stuckeberg field at all orders. At zeroth order, it transforms just via a shift. So if I put 0 here, I just get a shift with this new lambda. So this is kind of the simplest, quickest way to see that this is sort of a Goldstone mode for that symmetry that I couldn't realize and I thought of as broken. One interesting observation is that these Bernoulli numbers, they vanish for all odd orders. So for all odd orders, we'll have zeros here. We're not sure yet what exactly that means or if there's any useful implications of this. Good. So now let's look at the charges quickly. So obviously we want to now construct charges which will go into soft theorems. So let me take, the dressed field that I constructed and plug it back into the action in the bulk. Now you might notice immediately that I'm not actually changing the action, right? I'm formally, I'm just doing like a gauge transformation of this thing. So obviously these guys would drop out. So it's the same as the action without the Stuckelberg field. However, where it does get different is when you apply your covariant phase space formalism. Because if you insist that you apply it, on the tilted fields, you get something like this for the symplectic form, and then this will keep some information. So by the time you write your charge on a particular slice, you'll see that here I am keeping information about these Stuckelberg fields. Good, so this is just a drawing to kind of show you. So you originally defined this in the bulk on some slice, of constant time. Then you push it to null infinity in the standard way, taking your R to infinity and U fixed, and then you can go to scry with it. And then, of course, because it's a total derivative, which is a generic feature of these large gauge transformations, we can localize it on the 2D celestial sphere. Then we can define this tilted charge density from these charges. So here kind of to show you that this now I've kept the Stuckelberg fields in the definitions of the Q tilde. Then I can compute a Poisson bracket for these charges. So using these transformation rules that I was showing you with this funny operator, after a little bit of work, you find that indeed you get the expected charge algebra for the charges. So kind of the idea is that the dressed charges still satisfy the usual gauge algebra. Good, so now let me specialize a little bit to a slightly simpler subcase where we've done some very explicit calculations. So let me assume a simpler fall-off now. So I'm eliminating the log terms for a moment, and we can also have an expansion in U, which is the dual of the energy. And let me then assume that these overleading gauge parameters have dropped their logs as well, so the psi's are also dropping the logs. Then working in radial gauge, for example, what we have found, I wasn't able to put them on the slide, but you'll see them in the paper. At any order in this expansion, we have some very, very nice, quite simple recursion relations where you can see how the fields can be constructed from all the lower order fields, and thus everything will follow from the radiative data. Now, based on these recursion relations, you can then look a little bit at the fall-offs in U. Because you might have wondered, I don't know, if you're, especially if you're not very familiar with the topic, is why I'm looking at this R expansion when I showed you the amplitudes, it was an energy expansion that we had in the subleading theorems. Now, it turns out that the R expansion is very closely related to the expansion in the U parameter on scry, which is the dual of the energy. So very explicitly, so from this big table, let's just focus on the FRU component. So recall that this is the object that appears in the construction of the charges. So FRU is the relevant component of the field strength that we have in here. And notice that at different orders in the R expansion, we also have different orders in the power of U. So there is a direct connection between the subleading orders and the powers in R. Good. So once we've done that, we also have this nice hierarchy of charges. So there's a little bit of notation here, but the main idea is just that once you have these charges, so I've shown you some very general expressions, to all orders in R, but of course in practical calculations, you're going to want to truncate at some specific order in R. So here we see the coefficients of the lambdas, and at some specific order in your new fields. And the main idea here is that at each order we can recursively get, the expressions for the charges from the lower orders, and I think we have some expressions here. So they work out in a relatively simple way from the lower order charges, and the charge algebra is also truncated in a very natural way like this. So it never, if I say wanted to truncate to this level, the charge algebra will not take me outside of the truncation. So I can properly define, some closed Poisson algebra at whatever order I like to look at. And then we saw that this matches with some previous results for n equals 1, so this was just extended to one order in R, and electromagnetism. Good, so maybe I'll be very quick on this. So then we wanted to see if there's any interesting subsectors that have interesting algebras, as you've seen from Laura's talk as well. So something that in celestial holography people like to look at is these infinity algebra. So this is the Young-Mills version of the W infinity. And we follow the procedure from this paper to construct the generators of this infinity algebra. You can do them from these little charges R, which upon renormalization are just some charges that I didn't write explicitly, but they can be constructed from a subset of these recursion relations that we have there. So this tower of charges that go into the infinite dimensional algebra, we are finding them as well from our recursion relations. Now these turn out to be really related to the self-dual sector, and actually a quick way to see that is that if you look explicitly at the construction of these guys, you'll see that they depend linearly on some AZ bar, which you think of as a negative helicity, but then as you go to higher and higher orders, you only add positive helicity modes. So to kind of ignoring kind of the details of it, to kind of give you the big picture of the sort of algebras you get in this case, is that if you restrict to the self-dual sector, you have some infinite algebras, and similarly in gravity. If I go to the full, if I take all the charges, I just recovered the old, what I've expected, the gauge algebra. The interesting thing would be whether there is something in between the two. Can we preserve some more structure somewhere between self-dual and full? Because this has been studied very, very well. This is sort of the old story. So it'd be nice if there's anything in there, but I don't have anything very specific to say at the moment. Good, so let me now go back. So this was all just sort of the theoretical setup. So what we understand so far is that these symmetries that previously were just violating symmetries, we can now realize them properly. So let's go back to the soft limits and see what could we say anything interesting or anything useful for the soft limits from these symmetries. So generally the way amplitude split when you take one of these soft limits is that you have a universal part, which is, as I was showing earlier, just this nice factorization. But then you also have some non-universal part. So in the universal part, we also know that these S's don't depend on, for example, the helicities of the particles that go into the smaller AN amplitude. So generally what we expect is that only the universal parts come from the symmetries. Now there are some simple cases, like I was saying for self-dual and MHV amplitudes, where we simply don't have these non-universal terms. So in those cases, we have very nice relations coming from symmetries. But of course, it would be nice if we could say a little bit more. So let's focus on the subleading, and let me show you a nice example here. And I will look at a slightly more interesting scenario where just in the subleading term, we have a universal factorization plus something that we call quasi-universal. So what do I mean by quasi-universal? So there's this paper by Elvang, Jones, and Nakulich from a few years ago where they looked, so now I'm switching to QED. So until now I've been doing Young-Mills, but everything I've shown you can be kind of translated to QED coupled with sources. So let's go there because that's where we found this interesting example. If we couple QED with some higher derivative interaction such as this, it turns out that at the subleading order, you can actually find a sum of the standard factorization. So this is like the universal term. So this is the subleading universal term. So this is really a product. And then this S tilde, which you can either call it non-universal, quasi-universal, mildly non-universal. So the idea is that S tilde, it's no longer a product of some factor and the lower point amplitude, but an operator acting on the lower point amplitude. And it's written in this way, so this is just the spinor helicity notation, so it's just some products of momenta here. And this curly Fk is what we call a particle changing operator. So this curly F now, unlike the proper universal term here, it depends on what kind of spins or helicities I have inside AN. However, it depends still in a very nice form. So I didn't write the FK, but it's a fairly simple operator. It looks a bit like a SUSY type of operator or a spin changing operator. So this is why these are kind of terms that look somewhere in between universal and non-universal. So then the question is, can we get these from symmetries? And this was actually answered by Alok Lada and Prahar Mitra, again by looking at some symmetries that violate the fall-offs of the, thank you, yeah, I'll do that. That violate the fall-offs of the fields. So this specific example for the gauge parameter that I have here, you see it's got the leading order, well, the over leading order in R, and then some very specific form for the 0th order, where I see the U dependence. Now, the way they've seen that you can get both of these terms is by looking firstly at the symplectic potential. So this is what comes in the covariant phase space formula, so just the step before you construct your charge. And they split it, so again, I'm being very schematic, into the old part and the new part. So it turns out that the old part is just what would come from QED. The new part is what would come from these corrections, which then generate these quasi-universal terms. Now, the old part, as expected, gives the universal part of the subleading theorem. And generally, this new term is subleading relative to the old one. So if you look at the fall-offs of the fields that go into here, and you only allow for standard large gauge transformations, which preserve the fall-offs of the fields, what happens is that theta nu basically vanishes relative to theta old. So then you would never, if you only allowed, for standard large gauge transformations, you would never have the hope of recovering this S tilde here. However, if you allow yourself both of these terms, so the lambda and the R lambda, then there's an interplay between, the more sharp fall-off here with the R, the less sharp fall-off here without R, such that you really get enough information in the charge to really generate both. So both the universal one and the non-universal. Now, okay, all the hard work had been basically done for us by these people. So all we do now to kind of establish it as a proper symmetry in our extended phase space is that we just have to do, turn the crank, introduce our Stuckeberg fields, and then basically, again, very schematically here, I'm dressing all the fields that, appear in the calculation for the charges with my Stuckeberg field. So then the message then will be that we can get both universal and, mildly non-universal, quasi-universal terms arising from symmetries that act properly and canonically on the phase space. Another little lesson that we had was actually that different gauge choices can simplify things. So this was done in Lorentz gauge. As I was showing you earlier in the talk, we were working in radial and also light cone gauge. So this gives slightly nicer expressions for things. So that's a nice thing, that we're not very dependent on the gauge choice. And then the kind of, for future directions, the kind of hopeful thing is whether these sort of weird-looking overleading symmetries could actually give us some new structure in scattering amplitude. So we're not claiming, that everything will be universal and that we'll have integrability all over, everywhere in Young-Mills or gravity. But at least in some interesting examples, like the one I was showing earlier, there might be more structure than we expected, and that structure might actually come from some well-realized symmetries. It would be nice to look at loop corrections as well. And then, of course, the natural question is to extend it to gravity. Conceptually, the procedure should work similarly. Of course, the details are what will be a bit more difficult for gravity. But in the interest of time, maybe I'll finish now. Thank you.
Yeah, thank you very much for this nice talk. We have plenty of time for questions.
Yeah, hi. So here you include the Stuckelberg to account for this kind of stronger behavior of the gauge parameter. Yes. So why not relaxing the fall-off conditions on the gauge field to allow this gauge transformation?
Good. So actually, that's a very good question. So you're saying why not let the gauge field fall? Yeah. So we have the fall-off conditions on the gauge field itself. We kind of get them from very standard physical considerations, right? Like, so if we look at the electric flux and, you know, various things that we expect at null infinity, it kind of forces you upon this fall-off. So basically, to agree with physical considerations, we would like to keep the gauge field as it is in this case. But if you want to allow, you know, for more exotic things, you can think of, perhaps conceptually, you can think of this A tilde, this dressed guy. You can think of what as what you were asking as well. But it is important to separate them because the sort of physical gauge field that has the normal sort of electric field and stuff should be, should have the normal.
So further questions?
Sorry. Hi. Sorry. Yeah. Hi. So,
yes.
So if I understand correctly, you've got this infinite set of conserved charges, or infinite set of charges at the moment. And if you want to promote it to a useful statement for soft theorems, would you need to match an infinite number of parameters across spatial infinity, or is it just one parameter matching? And
Good. Do you mean for the gauge parameter?
Yes.
Okay, now that is a very good question. So because from the examples, okay, in principle, what we've written would allow for many different parameters. So at each order, we're not constrained and we could have different parameters. Now for some explicit examples, so like the one we have here that I was giving at the very end with these nice quasi-universal things, it turns out that you do end up using the same one for the same two orders. But I think, to be honest, we haven't looked at enough examples to tell you whether having different ones will give something.
Hi. Very nice talk. Thank you. I'm just a bit confused about how to interpret the symmetries. Are these symmetries of pure Yang-Mills or like Yang-Mills coupled to a bunch of Stuckelberg fields? So that would be like a larger theory, right?
Good. So yeah, maybe I should have spent a bit of more time here in the middle where I was. So let me go. Where is that? Yes. So the way you should think of it is that you could go back in the bulk, and in the bulk, you really only have pure Yang-Mills. So you can think of this A tilde as just a pure Yang-Mills field with all sorts of fall-offs like Kostas was asking. But then once I go to null infinity, it separates. So some of the modes of the field, it's good that you asked. So some of the modes of the pure Yang-Mills guy in the bulk, when we go to null infinity, we interpret them as sort of separate fields, like they split off. But in a sort of controlled way, they split off.
I see. So the physical part still behaves nicely under 1/r expansion.
Yeah, that's exactly the point. So the A itself, the non-tilde A, its transformation is unchanged. Yeah. So it's all absorbed in this size.
We have time for further questions.
I hope, like doing this analysis, you are never considering that the Yang-Mills coupling is weak, right? So because this is just some large R coupling or large U behaviors.
Yes, yeah.
Okay. So now what happens is that, like if you try to study say soft theorem for us, like pure Yang-Mills theory, like say soft gluon theorems, what happens is that the leading term, as you showed, is like 1/omega. But if you go at one loop, it goes like log omega by omega, and it will correct even the leading soft factor with more and more logs, like at n loop, it's log omega to the power n/omega. So you cannot, it's telling that if you go a large distance or small frequency, this Yang-Mills field does not make sense because of like the confinement kind of business. So basically, classically, I don't know how to make sense in the large distance, how the Yang-Mills fields really behaves like when the coupling is strong. So what are these really large R behaviors? Because for the full gauge field, if I solve it for strong coupling, even if I resum the loops, it always corrects this, even the leading soft factor, like more and more power, and which gives the large radius behavior is more and more ugly, like possibly log r to the power n over r for large, if I recursively solve in Yang-Mills coupling like the g to the power n order. So how to make sense of all this for a classical Yang-Mills theory when the coupling is strong?
Yeah, so what we've done explicitly here, we haven't really looked at the loops. So you're saying the loops will correct also the leading ones. Yeah, no, that's something I can't say too much about because we haven't explicitly looked at the loops. I think the procedure should be able, so if you look at the general procedure, we've really, in general, we haven't done, explicit soft theorems with this. We just looked at the symmetries, but in general, it seems to allow for log corrections as well. But I can't tell you anything explicit for the soft theorems because we haven't looked at the loop corrections. We haven't looked explicitly.
Okay, I don't see any further questions. So, but you also have the chance to ask questions during the break. So let's thank her again.